Internet, and thank you very much for the tuning into the Cloud Native FM podcast. My name is Saim Savdur, your host for this show, and you are watching the episode number 122. If you've been subscribing to this YouTube channel for a while, you have seen I am very much nerdy in the cloud native Kubernetes platform engineering and DevOps era. So now today I'm shifting focus toward my new interest, that is quantum computing. And I have a wonderful guest who will let me know what's happening in this ecosystem and why we are thriving towards a civilization where quantum computer become a big thing for us. So let me give you the introduction of my guest. Teo Körner is from the T Systems. Is a research and development engineer at the T Systems with a background in information system. Teo began focusing on quantum optimization during his time at T Lab and R&D unit of Telecom. In 2019, since then, he has been involved in projects that apply quantum-inspired solution to industry challenges, including vehicle routing and fleet optimization. Currently, at T System, Teo continues to explore the practical application of quantum computing in sectors such as logistics, finance, and manufacturing. Without any further delay, let me go straight to Teo. Teo, if I miss anything, it's your time to add.
No, thank you very much, Saim. It's my pleasure. Thank you for the invite. Looking forward for our conversation.
Awesome. Wonderful. I'm really excited about our conversation today because this is my episode number 1 with any guest from the internet on topic quantum computing. So I think we can try in a very basic level because audience might be very new to this topic. So can you provide a high level or basic overview of quantum computer versus traditional computer versus supercomputer?
Of course. Sure. So I'm going to start off with the classical computer and then going for supercomputer and then to quantum. So the classical computer is probably, the most obvious and easy to explain. So we are working with bits, so transistors that either flip between 1 and 0, but never anything in between. And we built, awesome logics, algorithms based on gates that do certain operations on these collections of bits. And that's the power we exploit for decades now, and that has fueled the unparalleled progress we have seen in computing throughout the last decades, from smartphones to our laptops to like Raspberry Pis or stuff like that. And the supercomputer is basically the, let's say, natural advancement of this technology when it comes to parallelization. So most of the supercomputers really excel or let's say add a new layer of power to this architecture by adding a lot of parallel compute threads, and then in the end, joining the results. So the architecture is still the same, but there's a lot of power through parallelization. There's actually a law in theoretical computer science, which is called the Amdahl's law, which says that at a certain tipping point, you will hit a limit of the speed up you can get by parallelization, because you have a lot of overhead to basically orchestrate and coordinate the different workloads. But as of now, we are obviously more than fine, and supercomputers have increased their power a lot throughout the last years. And quantum computing, on the other hand, is not just a natural advancement of the conventional computing technology, but it's a completely new domain of information processing or computing. So instead of using the bits and transistors that flip between 1 and 0 in quantum computing, we are exploiting quantum mechanical effects in qubits. So a qubit can be a lot of things. Let's say the hardware development is still ongoing. Let's see what the most efficient qubit will be at the end of the day. But from the information science perspective, the most fundamental difference is that we cannot just use 0 or 1, but we can use intermediate states. So yeah, it's not just the 0 and the 1, but any complex number in between. And these quantum computers are, yeah, you put basically a lot of these qubits on a QPU instead of a CPU, and you can build from the ground up completely new algorithms because the fundamental unit of information is so different to conventional computing.
Yes, absolutely. And I think for a lot of the folks who might be interested in this topic or be researching, they might think around, oh, this is so faster than we already have been accomplished over the decade, over the years, over the human invention in into the computing industry. So, Tio, the one natural question we have seen from everyone is speed the only thing that QC offer over the conventional computer system, or there are other things that QC can do that we haven't able to accomplish with traditional computers?
Mm. Yeah, that's a heavily debated question, and I think there's also a lot of misconception in especially mainstream media about the capabilities of quantum computers. And I've recently heard a talk from one of the, for me, very inspiring figures in the domain of quantum computing, which is Scott Aronson, which is a theoretical computer scientist, and I can highly recommend his talks about no-nonsense introduction to quantum computing. And he said quantum is not just a synonym for awesome. So it's definitely not a special a general purpose accelerator. Like you cannot just throw a quantum computer at any problem that is computational complex on a conventional system and expect a tremendous speed up or efficiency boost. So as I said, as we are talking about a completely new paradigm of working with information, that also enables a new paradigm of algorithms. So we are working with a gate set that is very different to classical computers, or adds some capabilities. So the algorithms designs are much different. And this is also where the idea comes from, that quantum is much faster, that based on these new algorithms, we are able to tackle certain problems that are very, very hard to tackle for conventional computers more efficient, which usually means in the context of complexity theory and in computer science, so how many steps it takes in the worst case to solve a problem with increasing size. We are able to define algorithms on a quantum computer that are more efficient when it comes to these time complexity questions. So we need fewer steps to solve certain problems. And of course, this at the end of the day may result or will result in a speed up by the number of steps that we need. But actually, a quantum computer from the, let's say, physical hardware level is a very slow device. Like one step on a quantum computer takes, at least from current estimations, way longer to execute one operation than on a conventional computer. So there's a little bit of juggling the terms, what faster really means, but it usually comes from the fact that the complexity theory just tells us, okay, there are certain problems that are more efficient to solve in the number of steps. And efficient can also, of course, mean not just time, but also, for example, energy input. So if I need fewer steps and a quantum computer is able to operate one operation at a lower energy input, then of course one could also imagine that the total energy input that I would need at a certain point to solve a problem gets lower. So that might also be an interesting consideration in the future if we are talking about some benchmarks like, I don't know, energy to solution or something to consider in performance boost in quantum computing in that way. But it's still, let's say, in research, how that in practice will look like.
Yes, absolutely. And I think as we're speaking today, I've seen, I think 3 weeks back, IBM launched first quantum computing data center somewhere in the Europe. So
Yeah.
that made me very excited. This stuff, even though in the research, is now companies like Google, Microsoft, IBM chiming in. I heard another news from the Microsoft. They built up a 64 qubit or something like that. So it's happening very fast in the very rapid race with the speed. So the one question from this, because I work with the cloud native technology for the CNCF spectrum. So do you know, is there opportunity for the quantum computer? We say environmental sustainability is a big issue, or the low carbon footprint is a bigger, it's a step forward for us. Does QC can be some sort of relaxation for us in that spectrum?
Yeah, that's, I would say, even a rather philosophical question to answer, because, of course, at the current state, with quantum computing being in research and does not solve any, let's say, relevant problems, the industry relevant problems today, any energy input that you have on a quantum computer is additional energy input. So, of course, today this is a little bit, let's say, looking into the future and how these debates and energy throughputs might evolve. But I'd say, like, quantum computing in its specific domain, that's also probably something we gonna talk to in a minute, where we actually can apply it. Is a new chance to tackle these problems in a completely new way than we do it the last decades. And that also brings, of course, a lot of potential. So, yeah, I mean, if we see the energy demands that supercomputing centers need today and will need in the future, I mean, you've probably also seen the debates in the US of companies actually thinking about deploying nuclear power facilities in order to fulfill their energy consumption needs. I think, I mean, it's still quite a fast stretch to say that quantum computer will help with that in any way, because especially when it comes to AI, there's no immediate way where we can say, okay, quantum computers will definitely increase the training efficiency or something of a model. So that would be a little bit of a too fast stretch or too optimistic statement to make. But I mean, still, it's a new computing paradigm. It's one of the very few new computing paradigms that we even know and that we can research on to tackle problems of the future. So yeah, I'm carefully optimistic, but I think obviously it all comes down to the progress that we will see in the next years.
Yes, absolutely. I think that these are the debates happening very often. I've seen the article, everybody talking about it. So I thought to ask you for these questions as well. But I think the one question that I'm trying, because we are in the November, as we recording this is 12th of November, and we're just a few days away from going into the 2025. So that's where the one natural question comes into my mind. How do you see the roadmap of quantum computing regarding, let's say, hardware or some of the other advancement in the algorithmic space, and what's happening generally, so where we are heading towards to?
Mm-hmm. Yeah, that's a very interesting question, and also I think one that from the time that I have that I have been in contact with the quantum computing ecosystem now, I think it's a heavy debated one, how we can, let's say, balance the long-term potential with short-term achievements. And I think this is also something where, I mean, quantum computing, of course, underlies the usual technology hype cycle. So we will see, or we have actually already seen some overhyping, where, as I said, a lot of players were just using quantum as a synonym for awesome. They were just throwing at, okay, quantum computing will solve all our environmental crises. It will basically be the one-stop solution for all problems of the universe. This is, of course, not true, but I would say it's the usual hype cycle. And we have seen tremendous achievements this year and also the prior years when it comes to scalable device rollout or quantum computing advancements. So I would say the most critical point or the most critical advancement that we still have to achieve from the hardware level, and disclaimer here, I'm not a physicist, so my domain knowledge on the hardware development is rather limited, but the most challenging part that we tackle today, or that the quantum computing industry tackles, is noise and how to correct this noise. Because these qubits that I talked about earlier, they are very, very fragile when it comes to any kind of environmental disturbances. And these disturbances can range from just radiation, natural radiation. It can be the interference, the unwanted interference between the electricity that goes through the system. So it's very, very hard and complex to control. And I have a huge amount of respect for the players in the hardware development that tackle these problems. But that's really the one thing that we have to solve in order to make a quantum computer useful. Because the noise, like, we need some error correction methods to correct the noise that is inherently always going to be there. And in classical computing, these error correction mechanics, they are well known, they are deployed everywhere, easy. But unfortunately, we need, as we are talking about a completely new paradigm, we also need completely new noise and error correction methods for quantum computers. Because one funny little strange thing about a qubit is if it's in superposition, so this intermediate state between 0 and 1, where all the or one part where the computational power comes from, if you measure it, if you look at it, it collapses back to either 0 or 1. And this basically makes all our conventional error correction schemes kind of useless, because they all rely on copying and controlling bits while in calculation. And Google rather recently has shown tremendous achievements in the error correction developments, in the way that they have shown for the first time in practice that correcting errors or correcting noise in a quantum system does not create more noise that ultimately makes the system unusable. Because that was a very critical point, that in order to implement these error correction protocols, you need more qubits. So you introduce even more noise. And there was let's say, for a long time, quite a debate if we will actually come to a point where the qubits are so reliable that you wouldn't increase the level of noise in the whole system by adding these error correction qubits. And this has been done in this year. The error rates in general are going down quite a lot. So I think these are very interesting advancements. But as I said, this is the one thing to challenge, because also from the algorithmic perspective, you can basically separate the algorithms on a quantum computer into fault-tolerant ones. So that basically theoretically assume that there's a quantum computer that works error-corrected and the way it should behave in theory. And then there are the NISC algorithms. So that's the era we are in right now. So noisy intermediate scale quantum devices, which means we are dealing still with noise that can't be corrected. And for a long time, so when I joined quantum computing in 2019, there was quite a lot of optimism that we will see an advantage from a quantum computer using NISC algorithms, and algorithms that are still influenced by noise. And these are usually heuristic approaches that are hybrid, so in, let's say, working classically with a quantum computer. But in the last years, the optimism has shrunk down quite a bit, to be honest, because these algorithms don't really scale that way. So I think we would either be good on focusing on fault-tolerant quantum computers, or using the quantum-inspired and NISC approaches for improving our classical computation. I think we can work through that in a minute when we talk about the applications. But Yeah, long answer. But I think the underline of it is just that I'm very optimistic seeing all the achievements that have been done this year, but I think we will still need quite a long breath, quite some patience until we see scalable quantum computers.
Yes, absolutely. And we all see in the news, and a lot of the research paper is coming out this year for correcting these noises in the hardware as well. And also, I think the IBM is recently, I've seen their roadmap, they're going exponentially with the qubits. And then this stops. Not we're not going for the more qubits. Let's figure it out to remove the noise as well. And as you mentioning during the conversation, Google has done incredible job. I've seen this is some there's doing some incredible work in this space as well. But a lot of the people who actually heard about the thing or might be excited about or might be overwhelmed with the information we are actually giving them, they wanted to know if the all this eventually comes down to the table and I'm accessing the quantum computing via my home, or a quantum computer might be in the Google or the IBM, and I'm just using virtually remotely from everywhere, what are the applications I can run and how eventually these will benefit me as a user of the quantum computer?
Yeah. Yeah, very good question, because I think that's also an area, as we said already, like there's a huge misconception what a quantum computer can do. Generally, if you look at it from a high level perspective, the three groups where there's an advantage expected, or at least there's the hope for some advantages of quantum computing, lie in simulation, usually of quantum mechanical systems, because that's quite kind of the home run use case, right? You have a quantum mechanical system. So what are you going to do with it? You're going to simulate another quantum mechanical systems, which turns out to be quite a huge part of, or an influential part of the work that, for example, pharmaceutical companies are doing. And that's actually also back in the 20th century, when quantum computing was described from a theoretical perspective, that was kind of the original idea. So simulating quantum mechanical systems. And I think that will also be the first one where we will see an actual quantum advantage. We might go through what actual quantum advantage means, but this is, I think, the best use case where we have a straight roadmap, what needs to happen until a quantum advantage is there. The other two areas, and I think these are a little bit more under debate, are optimization and machine learning. In optimization, people have basically or are coming up with ideas to exploit these advantages that we get from the new computing paradigm, and in terms of the complexity theory that we talked about in some minutes ago. They came up with ways to make use of these advantages for hard and NP-hard optimization problems. So again, optimization problems, like it can be anything from route optimization to, I don't know, optimizing your supply chain, which is basically the same thing, but you know what I mean. So hard, conventionally solvable optimization problems. And I'm saying that this is a little bit of a mixed story, because I need to take a step back here. When I introduced the quantum computing fundamentals, I was referring to gate, and this is also, let's say, the most universal and most, from the potential, most powerful domain of quantum computing. But there's also something called quantum annealing, or adiabatic quantum computing, which has a little bit of a different idea. It still uses QPUs and qubits and superposition entanglement as the fundamentals, but instead of building algorithms based on gates, it uses a concept of energy minimization. So you would translate your optimization problem into an energy function that, or let's say a mathematical representation of an energy model. and then you would let the quantum annealing chip basically naturally find the most optimal solution. It's rather similar to what is known as simulated annealing, for example, in conventional optimization theory, but this is also some domain which belongs to quantum computing. There's a company, there are several companies active there, and there are some promises there that advancements in the domain of optimization will be there. But from the theoretical side, there is not really a whole lot of proofs that this will actually happen anytime soon. So quantum annealing is a heuristic, so it's like a method to get to a rather good solution, but not to a guaranteed best solution. So you would never really find a let's say a general proof that this is proving that this is giving any advancements. And on the gate-based side, you would have Grover's algorithm, which is one of the algorithms that has a theoretical advantage on a quantum computer, but is still under debate how much of the theoretical advantage is actually translating into practical speed up. And this is basically the same story for machine learning, because quantum machine learning is also still a very, very broad research domain. So they are basically all combinations of methods and technologies in the pot, and some promising directions, but I would say it's similar to optimization, that we still need some more time to digest or to analyze and practice if this is coming to any kind of speed up anytime soon. And these are the three groups. And of course, a lot of industry potential falls in these groups, especially optimization. Like optimization is present in more or less every industry. But I think this is to be taken with a grain of salt, because, as I said, if we don't have a provable advantage, I think some expectation management is really key to stay reasonably active in the field.
Yes, absolutely, absolutely. And there are some companies doing some great work in the QC space as well, and also I think the health industry in particular, where cancer, Alzheimer's disease, and also in the environmental aspect is accurately expecting that tsunami or some sort of storming, where might be some of the applications of QC really helpful. And I think we're heading towards the QC civilization, that's for sure. How long would it take? It's a question, but we've seen there's something happening in this ecosystem, and eventually people become upstream with the quantum computing. So, Teo, few words about number one question might be folks are hearing to us in a few minutes, and a few words around. In CNCF, we have a lot of the platform working groups specifically dedicated for the technologies. In quantum computing, what are the communities I can involve in to see what's happening on the daily basis? Is there are some communities internet exposable to everyone for us, and everyone for us to can see what's happening in there?
I think let's say identifying people, inspiring people that do the no nonsense work in quantum computing. So let's say from a very good theoretical knowledge, and applying this to trends that are happening. I always think this is the best way to keep track, because you would always get a realistic and a good reasoning of what recent advancements mean. I can, like, as I said, Scott Aronson for me is a very, very good source there. That he has a blog that is very a good read. But there are also, of course, way broader communities. There's like a Stack Overflow quantum type of thing, where people just engage and discuss potential and limitation. There's the communities around some SDKs like Qiskit, which is open source but heavily supported by IBM, which also provides great learning material. So I think these are the good ways to start. But then again, I would say it's very, very fundamental if we talk about quantum computing, to balance pragmatism with long-term potential. And especially in industry, I think this is the key to make something meaningful out of the initiatives and the communities. Because long-term potential is great, but if you can't translate it into something that is providing any kind of measurable impact in the next years, industry communities or industry initiatives will have a hard time surviving. And this is also what I am mostly focusing on. So how to balance these paradigms of pragmatism and optimism, basically.
Yes, absolutely. This has to be taken into consideration, specifically if things are in the experimental phase. Striking the balance is a very important thing. So before leaving you off, I have 2-3 minute final left for this conversation. Is Teo, I know you work in the T systems. Can you tell a little bit about what's actually happening from your company's perspective in the QC space?
Yeah, of course, with pleasure. So as I said, I have learned throughout the last years that the balancing between the hype and the long-term potential and the pragmatic possibilities that we have in the upcoming years is really essential to keep track of such a technology, such a fundamentally new technology in industry. So what we are doing in T Systems is a mixture between keeping an eye on the progress that is being made and realistically evaluating the potential and limitations. And the other thing is called it's under the larger domain of quantum inspired technologies, which is kind of a cool development where research in quantum computing has fueled progress in conventional computing. So under the hood, you are still running stuff on a conventional computer, but you are using input models and methods that were inspired by research on quantum computing. So at the end of the day, you will definitely not have any quantum advantage from that, logically, but it's a great way to already learn the fundamentals of quantum computing and apply it to actual industry problems by still limiting the risk of the big if, when and where a scalable quantum computer will actually appear. And that's most of the work I and we are actually doing. So helping customers, let's say, untangling the hype and seeing like, is there some potential in the technology for you at all? Like, as I said, it's not a general purpose accelerator, so there needs to be some fit for industry or for that specific industry in terms of relevant problems and algorithms, and then taking them on a track from, okay, this is the long-term potential, but what is something we can actually do with quantum-inspired technologies today? And then we are mapping these industry problems into formulations that are ready, quantum ready, so to say, but still running them on conventional hardware to actually see or let the customers and ourselves see the models work. These are the results we get currently, and yeah, we can still have some impact with that today, even though a quantum computer is not fully ready.
Awesome. Thank you very much, Teo, for explaining all these kind of stuff. So this is a very natural topic for me as well. So I take an eye out in as well. And also T system appearing on your logo. You can go into the website and check out what's an offering available as of today. But Teo, thank you very much. This is our beginning of this YouTube channel to keep track of what's happening in the QC space. So you are a very educational resource for us. So I keep looking at you, what you are throwing in the community and how things are shaping up. So hope you enjoy the conversation all. If you have some question, put them in the YouTube chat description, and Teo and I will be happy to answer those as well. With that, thank you very much for listening this newer podcast on QC and hoping to meet you in the near future. Bye bye everyone and stay safe.